Welcome to the deep dive. Today, we're looking into something really, really exciting, a scientific development that tackles one of the biggest issues we face, getting fresh water. I mean, just imagine taking salty seawater, ocean water, and turning it into clean drinking water with, get this, only sunlight. No electricity involved at all. So our mission for this deep dive is pretty clear. We want to unpack the science, the really groundbreaking stuff behind this invention, and, understand what kind of impact it could actually have. We're pulling this from some brand new research just published in ACS Energy Letters. It's a top journal, so this is cutting edge stuff. We'll give you the shortcut, basically, to the key takeaways without you having to wade through all the technical details. Okay, so let's start with the big picture, the basic challenge. Our planet's covered in water, right? But here's the catch. Over 97% of it is salt water. You just can't use it for drinking or cooking or farming, not without a lot of processing anyway.
Yeah.
And that really highlights this huge, urgent need globally for fresh, drinkable water, especially in places already struggling with water scarcity.
That's absolutely right. And, we do have large-scale desalination plants. They work. They remove the salt, make seawater drinkable.
Yeah.
Been around for a while.
Sure.
But the thing is, they have some pretty significant downsides. They use a ton of energy.
Yeah, right.
And they need really complex, expensive infrastructure. So those things, they're major roadblocks to getting them everywhere they're needed, like in developing regions or just remote spots.
And that's exactly why this new development is, well, it's potentially such a game changer. We've got this team of scientists. They've created something new. It's like a sponge, an aerogel, actually. And it turns seawater into drinking water just using sunlight. That's it. Feels like, I don't know, a real step change, not just a small improvement.
It really does. And what makes this material so different is its structure. It's a 3D printed aerogel, but it's designed very precisely. It has these microscopic vertical channels running through it. And that specific engineering, that structure, is absolutely key to how well it works. Scientists have been playing around with similar ideas. Solar sponges, they sometimes call them.
Right, I've heard of those.
Yeah, so there were earlier things like hydrogels. Those are sort of soft, filled with liquid, and other types of aerogels, which are more rigid. They showed some promise, definitely.
Oh.
But the big problem was they often didn't work as well when you tried to make them bigger. They lost efficiency as you scaled them up. And that's why this new aerogel is such a potential breakthrough. It seems to overcome that scaling issue.
Okay, that makes sense. So, yeah, given those past problems with making them bigger, how does this specific design, this new one, actually work? How does it manage to be so efficient?
So what the researchers did was create this special paste. It's got carbon nanotubes in it, those tiny, strong carbon tubes, and cellulose nanofibers, which are basically just really, really fine fibers from plants.
Yeah.
They mix this paste up. Then they 3D print it onto a frozen surface, layer by layer. So each layer freezes and solidifies before the next one goes on.
Clever.
Yeah, and the result is this sponge-like block, but it's got these perfectly arranged tiny vertical holes all through it, about 20 micrometers wide, so really small.
Wow. Okay, so you have this special sponge. How do you actually use it to, clean water in the real world? What's the setup?
It's actually incredibly simple. Picture this. Yeah. You just have a cup, basically, filled with seawater.
Oh, right.
You put a black piece of this aerogel inside the cup, and you cover the whole thing with a curved, clear plastic lid, like a dome.
Okay, I can picture that.
And the process is just sunlight.
Yeah.
The sunlight hits the top surface of the black aerogel and heats it up.
Right.
Now, crucially, only the water turns into vapor. It evaporates, leaving all the salt and impurities behind in the main body of water and the sponge.
Ah, okay. The salt stays put.
Exactly. Then that pure water vapor rises, hits the cooler, inside surface of the plastic cover, and condenses back into liquid water.
Like condensation on a cold drink can.
Precisely. And then those pure water droplets drip down, and you collect them in a funnel or a container underneath. It's like a tiny, self-contained water cycle powered by the sun.
That's really elegant. And the results, did it actually work well outside the lab?
Yeah, they tested it outdoors under natural sunlight. And this simple setup, remember, no electricity, no complex pumps or anything.
Right.
It successfully produced drinkable water within hours. Specifically, they measured about 3 tablespoons of fresh water after just 6 hours in the sun.
3 tablespoons in 6 hours. Might not sound like a huge amount initially, but considering it's just using sunlight and basic materials.
Exactly. Getting potable water straight from seawater, powered only by the sun, in a matter of hours.
Yeah.
that really shows the potential here.
And it directly tackles that scaling issue you mentioned earlier.
Yes, that's the key breakthrough, really. That question of, how do you make a technology truly accessible if it only works efficiently when it's small? That's been a major hurdle.
So how do they prove this one scales?
Well, the team specifically tested square pieces of this aerogel. They tried different sizes from quite small, about zero point 0.4 inches or 1 centimeter across, up to roughly 3 inches or 8 centimeters wide.
Okay.
And the crucial discovery was that the larger pieces evaporated water just as efficiently rate-wise as the smaller ones. There wasn't that drop-off in performance.
Oh, that is significant.
Yeah, one of the researchers, Shi Shen, put it very clearly. He said, our aerogel allows full capacity desalination at any size.
Wow.
And he added that it provides, and this is a quote, a simple, scalable solution for energy-free desalination to produce clean water.
Simple, scalable, and energy-free. That's the hat trick, isn't it?
Pretty much. It suggests this isn't just some lab curiosity. It really could be scaled up.
So if this genuinely scales, like they say, I mean, the potential impact for global water access is just enormous. Are they looking at the next steps now, like cost or how long these things last?
Absolutely.
Yeah.
That's the next logical phase. While the science, the efficiency, the scalability look really promising,
Yeah.
the focus is shifting towards those practical things. Can it be mass-produced cheaply?
Right.
How durable is the material out in the real world under different conditions?
Yeah.
What about long-term maintenance? Those are the questions they need to answer to really push this towards widespread use.
Makes sense. So thinking about this for you, the listener, what this really means is that we're seeing a potential leap forward. It's not just about a fancy new material. It's more about how really precise engineering down at the nanoscale, combined with something as simple as sunlight, could potentially, democratize access to something as basic as water. It kind of challenges our ideas about needing massive, complex infrastructure for solving global problems sometimes.
It really does, and it leads to some interesting thoughts, doesn't it?
Mm-hmm.
Like, if you could take this technology right now and put it anywhere in the world, where do you think it would make the biggest, most immediate difference? And maybe stepping back even further, what other big problems that we face every day might have simple solutions hiding in plain sight, just waiting for a clever bit of science like this one?
That's a great question to ponder. Definitely food for thought. Thank you for joining us on this deep dive today. Hopefully, thinking about innovations like this, these sustainable solutions, gives you something interesting to consider.